Welcome everybody to today's webinar, which is about tuning, about performance tuning. So let's take a quick look at the agenda. So we have split today's presentation into 3 parts. The first part is about tuning opportunities. So tuning starts long before you start the solver, and there are many aspects and opportunities within your system architecture about tuning. So we will cover a few aspects, talk about the most important ones, and then in the second part, we will talk about parameters, about Gurobi parameters, so things that you can change, things that you can adjust to change the behavior of the solver, to change the behavior of the algorithms. And then in the third part, we will talk about automated parameter tuning. So Gurobi has a tool that allows you to tune parameters in an automatic way, and we will talk about this and see how you can use it to get the most out of your models. So let's start by taking a look at something we call the optimization workflow. And this workflow is something that you will usually have always somewhere within your optimization system. And it's a cycle, and we will see why that is in a few minutes. So usually you start with a problem instance. So there is a problem that you have to solve. And it's usually connected to a lot of data that is required to solve this problem. So let's say maybe it's a decision problem. Usually it's a planning problem. So this problem with all its data is the input to a model generator. So a piece of software that takes all the data and creates a model from it. So after the model generator has finished, you have a model instance. And this model instance, so an objective function, a set of constraints, and variables, this is the input to the optimizer. So you give this model instance to Gurobi, and Gurobi will solve the model. And after this is done, the process of solution retrieval is there to transfer the results from the solver back to your user interface, usually for further analysis. And sometimes this is not the end, but sometimes it changes the problem instance. For example, you can adjust your data, you can adjust the problem, you can adjust the objective, whatever you want to do, and the cycle starts from the beginning. So if you do manual planning, for example, you usually go through this cycle multiple times. Now we're going to talk about various aspects on these different steps within this workflow. So we call this tuning opportunities and a few aspects. And it starts already in the system architecture. So the whole architecture of your software system, so within the hardware and the software, can contain a lot of performance issues. And the most important message here is to find out where you actually can improve performance. It is very important to measure runtimes. So not only in the beginning, but in every part of the process. So first you should measure the time that it takes to collect and process input data, because this usually takes some time. You have to connect to your data sources, to your database, to wherever the data comes to as an input for your optimization model. Then it will take time to build the model, so build up the whole model structure that is then the input to the solver. Then of course there is some time that is required to solve the model. And what we always recommend is, for this part, keep log files. So the Gurobi log file is a valuable source of information that you can use to find out where time is spent, and maybe also later to find out what can be improved. It's very important to see that optimization, so every part of this process, needs physical resources, so CPU, processor, and memory. So the first thing you should be aware of is that you really need this physical resource. So be aware of concurrency. So there might be other processes running on the same system. There might be other virtual machines running on the same physical machine, and those can consume resources as well. But of course, in a modern software architecture on the system, there might be, for example, other containers that use hardware resources themselves. So let's look at the hardware aspect first. It's very common that people contact Gurobi support with hardware questions. For example, during the start of a project, the question is usually, I'm going to invest into new hardware. So I'm going to buy a new machine. So what is the best machine for my optimization application? So this is a very common question. But also if you have an existing machine, people usually ask, so how can we improve performance? For example, will my model solve faster with more memory? Or if you're looking for a CPU upgrade, the question might be, which CPU models do you recommend? Which are best for optimization applications? Maybe later you already have your models, or you're looking to solve multiple models in parallel, and then the question is usually, how many models can I solve in parallel? So maybe you're looking for maximum throughput. So it's a very common use case that people have lots of models that they want to solve, and the question is, do we solve them sequentially, one by one, or do we solve multiple models at the same time? So the answer to all these questions, unfortunately, is usually it depends. It's not so easy to give a general recommendation that is right for all models, but it's really important to take a look at the model type and how it is solved in general. So as a general guidance, we always say if you solve a large mixed integer problem model in parallel, usually you get the best performance from a system with the fastest possible clock rate, so from a CPU perspective, and for channels per socket of the fastest available memory. This is a general rule of thumb, but there might be models that are a bit different and that, for example, don't benefit that much from parallelism. So there is no hardware recommendation that is right for all models. And as part of your regular maintenance and support for your commercial license, you are welcome to contact support, for example, by email at support@gurobi.com to discuss your specific models. So we can take a look at these models, run them on our machines, and find out what hardware we would recommend. So remember, in the very first stage of this optimization workflow, we have the model generator. And the model generator needs data access. And one very common support case at Gurobi is people approach us and say, Gurobi is slow. But the reason is not really that Gurobi or the solving is slow, but it's because the model building takes so much time. So accessing the data, putting everything together and building the model takes, here is an extreme example, for example, 30 minutes, but the model is solved within a few seconds. So in this situation, performance tuning means not to tune the solver, not to tune anything that comes in a later stage, but to start already at the beginning with the question, so how do you access your data? How does it work and how much time does it take? For example, sometimes you have long lookup times. So if you connect to various data sources and you retrieve the data that is required to build the model, this can take a lot of time. So usually it's a good idea to do some pre-processing here, to collect the data, maybe in a batch process, put everything together, and then you start to generate your model. But also it is quite frequent that people don't do caching or they do redundant queries. So sometimes you have to take the same data points again and again. And in a situation like that, you don't want to query them again and again, but you want to find some kind of cache that you can use to look up data that you already retrieved in a previous step. It's also quite common that people add single elements to a model or retrieve single data elements to build a model. So usually it's a good idea to do batch processing in the sense that you build, for example, many parts of your models at once. So if you already know that you have 1,000 variables, 1,000, for example, binary variables that you need, why not create them at once? This is usually much more efficient than creating them one by one. So the interesting question here is, if you would remove all Gurobi API calls, how long would it take? I mean, it's a theoretical question because, of course, you cannot just remove the API calls because you work with objects that you created in a later stage of the model construction. But this is the general question: how much time do you spend in everything that is outside of Gurobi? So once you found a way to do this in an efficient way, the next step is, of course, the model construction. And Gurobi has many different APIs, and we say each metrics generator has its own pitfalls and best practices. So the question is, are you using the most efficient way to build expressions? If you build models, usually what you do is you build not only the objective function, but a lot of constraints, and you build the left-hand side, and it means you build most of the time linear expressions. And you can do this in an efficient or in a less efficient way. So you should really look for bottlenecks here. So it's a good idea to measure runtimes, for example, for each group of constraints that you create. Our object-oriented interfaces are a thin layer on our matrix interface. So that means the overhead is usually small, but if you do it in a, for example, step-by-step way that takes a lot of times in smaller steps, maybe it's a good idea to improve here. And we can help you with that. What we already do is, not only with the object-oriented interface, but in general, are lazy updates. So since you work on the same memory that is used by the solver, it's a good idea, for example, to create variables all at once. So then create the objective and constraints. So this is the workflow that we propose. Create all your variables at once in the beginning, then you set the objective function, then you add your constraints, and then you call the optimize function. In fact, you could also switch these. So you can also create your constraints and then set your objective functions. That shouldn't make any difference. But the general idea is do not go back and forth. So create the variables at first, and then you go from there. All right, so now that you created your model and you call it optimize, what can happen to slow things down? And one important aspect is, of course, memory. So if you don't have enough memory, this can really destroy performance. For example, virtual memory on disk is far slower than RAM. So if your model requires, let's say, 32 gigabytes of memory because lots of threads are running and there is a lot of parallelism, it requires more memory. And if you don't have enough physical memory on the system, your operating system will extend this physical memory to virtual memory, which is on disk. And this is much slower because disk access takes so much more time than access of the memory itself. So during this process, and especially during development, you should really use system monitoring tools to take a look at how much memory is actually used. So for each operating system, there is a tool for it. On Windows, there is, for example, the task manager. On Linux, there is the top command. And this gives you a good idea on how much resources are needed to solve the model. And if you run short on memory, you can do something about it. For example, you can manually reduce parallelism. You can, for example, decrease the number of threads. Threads is a Gurobi parameter, and it's not helpful for all models to use all physical CPU cores that you have, or you use a high number of threads. And if you decrease the number of threads, you can also decrease the memory that is needed. Gurobi also has its own system to extend memory. We have something called a node file. So in a situation where the memory problem arises in a later stage for a MIP model during the tree search, you can use the node file start parameter to let Gurobi write nodes to disk to pick them up at a later stage. And this is much more efficient than relying on the operating system to do that. But it's only helpful for certain models. Usually memory is cheap. No need to skip. So make sure that you have a machine that has enough memory for your model. And again, this is something where Gurobi support can help you. So if you're not sure how much memory it takes, you can send over your models and we are happy to take a look. Another important aspect is network communication overhead. So in a situation where we have a client-server architecture, it usually means you need to transfer data and of course the model. So for example, if you use the Gurobi compute server, be aware of potential network issues when retrieving data or accessing the Gurobi compute server, especially networks with high latency. It means you send messages back and forth over the wire or over the air, and this takes some time. So if you use a lot of API functions, this may take a significant amount because it's a protocol that requires that a message goes to the server, is processed, and goes back. In the last release, we have added communication statistics to our log file. So what you can do is at the end of the process, you can take a look at the log file, and there you have some communication statistics. So you can see the total amount of data that was sent and received from client to server. You can see the number of messages, and you can see the average throughput. So this is all in the log file, and it's usually helpful to take a look to find out how much data was actually transferred. Before we move over to the next topic, we really need to talk about performance variability. This is the most important aspect when we talk about benchmarking models. Actually, it happens all the time. If a MIP solver solves a problem, it often needs to throw a dice, flip a coin to decide what to do next. So if there are multiple paths that you can take, you need to decide somehow where to go next. And what Gurobi does is it uses a pseudo-random number generator that produces the same series of random numbers for the same random seed. And the good news is this seed value can be changed. So there is a parameter which is called seed. So you set the initial value, and this determines the numbers that are generated throughout the process. So playing with this seed parameter helps you because you can find out how much these random algorithmic choices influence your runtime. And this is something that is called performance variability. So the same model on the same machine with different random seed values can take very different values for the runtime. And it's normal. So this is something that you should always expect, especially for MIP models. For some models, it's not an issue. Some models behave pretty stable, so there is only a small variance in runtime for different seed values. But we also have models there where the difference is huge. So some models you can solve them within seconds or minutes for some seeds, and some take forever. So this is a behavior that you should know for your model. And in case you suffer from performance variability, you need to take this into account for benchmarking. So if you benchmark performance, so if you take a model and you measure runtimes, do two different things. First of all, it's always a good idea not to benchmark only a single model, but use different instances of the same model type, and of course run the same model instance with different random seeds to find out. Yeah? So you can measure this yourself. You can see the effect, and this helps you to find out, okay, how much difference in runtime is going to be expected. And this also gives you a hint on, for example, what difference you can expect on the different systems, because CPUs can be different, systems can be different. So this is something that is always to be expected. The next aspect is numerical issues. So this is something that also happens on a computer because of floating point arithmetics. And numerical issues have also a huge impact on the performance, and not only on the solution time, but also on the solution quality. So for many models that have numerical problems, it's often very helpful to, for example, reformulate the model or rescale the model or change something in the input data. We don't cover this topic in this presentation. We had a recent webinar about this, and we also have a guide on numerical problems. So you can access all of this on our website. This is the numerics PDF that you can download and take a look. And you can also look at the recording of our recent webinar. This was given by my colleague Daniel, and it also contains a lot of interesting information about numerical problems. So if you do profiling, if you measure runtimes, you can do this, of course, as part of your application. But if you want to find out what is really the performance that is taken during the solve, so without the application, it's always a good idea to use the model generator and to export a model file. So you export an MPS file, and then you just run it through our command line interface, so with Gurobi CL. So you don't need the model generator anymore, and you just use the plain model. So the whole model structure is there at once. And see if solution time are much faster. If yes, then it's a clear sign that the problem is somewhere else during the model construction. So the interesting question when you do this is, what algorithmic part is the bottleneck? So there are many different parts. Of course, this also depends on the model type, and the log file is a helpful tool to determine where time is spent. The whole process usually starts with Presolve. So this is the stage where we reduce the model, where we try to simplify it and create a smaller representation of the same model that is used in later stages of the process. Then, of course, we have the solving phase. So for LP models, this is the problem itself. For MIP models, this is the LP relaxation, and this also takes some time. Then there is the root node. So at the beginning of the tree search, there is node 0, the root node of a MIP problem. And this is a phase, for example, where we generate cutting planes and apply certain heuristics. So this is a stage that can also take some time. Again, this depends on the model type. So the latest stage usually, or the next stage or the final stage, is the node processing, the tree search. And the log file contains the runtime. So you can take a look and you see, okay, how much time is spent during pre-solve, solving the LP relaxation, and so on. So the logs really help you to identify the bottlenecks. And we will have a few examples on a few later slides. So this is the most important stuff about the general model construction, model building within the workflow. And now we take a look at the parameters. So the ways how you can adjust parameters, how you can influence what Gurobi does with your model. And Gurobi has a huge number of parameters. So it's roughly 120 right now for the latest release 7.5. And you can group them by functions. So they do very different things. Something that you are very likely to use are parameters for termination. So when does the solver stop? When is it enough? So sometimes this is wall clock time. So you say, okay, we spend at most 10 minutes to solve this model, or you solve to a certain MIP gap. So this controls when the solver finishes and returns. Then there is a set of parameter that is about tolerances. So as I already said, in a world of limited numerical precision or accuracy, tolerances are very important to do stable computations on computers, and there are a lot of parameters that you can change, although we don't recommend to do that. So the tolerance values were chosen very carefully from experience, so usually you wouldn't touch them. There might be exceptions, but this is very special, so we usually recommend not to touch them, at least not in the beginning. Then, of course, there are parameters that affect the behavior of our algorithms for continuous problems or continuous problems that we solve within integer problems. And these are parameters regarding simplex and barrier. So you can change, for example, the pricing or the norm. And for barrier, you can, for example, change the crossover strategy. For MIP models, there is a very important parameter, which is MIP focus and a few more. So you can change the focus of the search. So the focus can be either find new feasible solution or improve existing feasible solutions or improve the bound. So and that changes what effort is spent in what algorithm. And for many models, it can be helpful to try out to change this. But again, we have an example about this on a later slides. Then there is cutting planes. This is also closely related. So cutting planes affect the bound. So this is something that's really worth looking at. Then also the behavior of the automated parameter tuning tool is also controlled by parameters. So for example, if you use this tool, the total time that is spent to tune the model is controlled by the tune time limit parameter. Finally, besides a few other parameters that we'll not cover today, you also control distributed optimization through parameters. So you can use multiple machines to solve the same model or to tune the same model, and the parameter that you usually use is called worker pool. So you define a set of machines that is used and they all work together on the same set of models. So, okay, we have 120 parameters. Not all of them are related to performance, but with 7.5, it's roughly 57 that are related to performance. And most of these parameters have multiple different values. So you can send your model, we can take a look, and we could probably tell you which parameters work best, but it takes a lot of time. So the parameter space itself is huge. And sometimes we also need to try. We don't know. We cannot just look at the model and know what parameters work best, but we really need to do this ourselves. We need to do benchmarking, and it's a mix of maybe automated tuning and a lot of experience, especially when looking at the log file. So again, it's very helpful to look at the log file to find out what makes the model difficult. So that's why we also talk about automated parameter tuning tool in the next section. So let's start with the first important algorithmic part of Gurobi, which is Presolve. So Presolve takes some time, and it's also a trade-off. So what you do is you spend some time up front, and you hope that you can simplify the model, that you can reduce the model to a simpler representation in order to speed up things in later stages. But sometimes it's helpful to reduce or to increase the effort that is spent during Presolve. So if you think that you spend way too much time in Presolve, maybe you can just try to reduce it by adjusting the Presolve parameter. So you can set it, for example, to a value of 1 so that you spend less time, or you can increase the effort that is spent. And it's really hard to say if this is helpful or not, so this needs to be tested, usually for every model. There are also other parameters that can be used to fine-tune Presolve. For example, you can adjust the number of passes, of cycles that are applied at the beginning or during Presolve. You can control the aggregator, so that is used to replace various parts of the model, for example, using existing equality constraints and so on. So there are multiple parameters, especially if Presolve takes more time. It's a good idea to take a look at these parameters and see if it helps to change them. So for the continuous algorithms, so simplex and barrier, the default is concurrent. So that means since we don't know upfront which of these algorithms work better, we do a horse race. So we use them at the same time. So each algorithm works on the same model, independent of each other, and we stop whenever the first algorithm finishes. So usually these are two flavors of these algorithms, which is deterministic and non-deterministic. So non-deterministic means you let them run on the machine in parallel, and whenever the first one finishes, we stop the process. Sometimes this is not so helpful because you really want to have the same behavior all the time. So for example, if there is some other process running on your machine and the runtimes are very similar, sometimes one algorithm may be faster and sometimes the other. And if this is something that you really don't want, you can also select the deterministic versions of concurrent. It takes slightly more time usually, but this gives you the same result for the same model on the same machine. But of course, each algorithm needs its own memory, so this is also something that requires more memory. So the defaults that we use for continuous models are these. So for LP, if we solve LP models, we use non-deterministic concurrent. So we really do a horse race and we really run the models in parallel and we stop whenever the first one finishes. For QP problems, this is barrier. So we don't do concurrent, but we use only barrier algorithms using all available threads. For MIP models, there is this initial stage solving the LP relaxation. But for MIP, it's also very important that we start with the same optimal basis every time. So by default, in this case, we use deterministic concurrent. It really depends on the model. So sometimes, depending on the model size, we only do dual simplex. And by default, for solving the MIP nodes, we only use dual simplex. So you can adjust this with the method parameters. And it's usually a good idea to play with this parameter. You can also change the method that is used for MIP nodes, but usually you wouldn't play with this because the node method parameter hardly helps. So dual simplex is really the best choice for most MIP models. So the interesting question is, okay, so which solver is fastest? And as I said, we use concurrent LP, but for example, if you compare concurrent LP with only dual simplex, concurrent LP may be slower than dual simplex. And this may seem surprising, so the question is, why is that? So the important thing is, concurrent optimization is of course fastest on average, but it's never the fastest for a specific model. So if you think about it, it works like this. So if you run concurrent and barrier wins, that means barrier didn't use all available threads, so concurrent wasted threads on simplex. So in a situation like this, it might be a good idea to switch over to only use barrier, and barrier can use multiple threads at the same time, and this is usually helpful to further improve performance. If simplex wins, that means even though you were running barrier at the same time, simplex was still faster. So everything that barrier did, especially accessing memory, so they were fighting for the same resources. It's also a matter of concurrency. So if simplex still wins, then simplex had to fight for resources, and that means it might be a good idea to switch to simplex all the time. Of course, like I said, concurrent uses much more memory, so each algorithm needs its own memory. So yeah, it's a good idea to try out if concurrent is really the best thing for your model. In a situation where memory is tight, of course, we always recommend to use only dual simplex because it uses much less memory than barrier. Yeah, we have an example. Here it is. So for example, we use non-deterministic concurrent for LP. So we call the optimize function. And in the first run, it solves with dual simplex. And it takes 3.75 seconds. And the optimal objective is printed. And if you query a certain variable, you get a value. But if you run the model on the same machine a second time, barrier is fastest. And the solution is slightly different. So in both cases, we get an optimal solution, but it can be different because there can be a lot of different optimal solutions for the same problem. And this is quite common. And the reason for that is that it's non-deterministic here. So this is the default. So if you don't want this, and it's rare, you should really explicitly select an algorithm that you always use the same algorithm for this model. If you want to use a deterministic method, this is also controlled through the method parameter. So you can choose simplex, you can choose barrier, and you can also choose the deterministic and non-deterministic versions of barrier and simplex, or for example, only primal and dual simplex by setting a certain value for the method parameter. There are also some other parameters for continuous algorithms, and you should be aware of them. It's not so easy to improve performance by just changing them. So for most models, it doesn't help. But of course, if you're really looking for the best performance for your model, sometimes it's really worth looking at them. For example, for simplex, you can adjust norm, and you can adjust the pricing strategy. So those are the two most common simplex parameters that you can change. And also for barrier and crossover. So crossover, this is the step after barrier to get to an optimal basic solution. You can change a few things. So you can, for example, change the crossover parameter and the crossover basis parameter. All right, so let's move on to integer problems. So now we're solving problems with integrality constraints. So what makes it difficult? Again, it's helpful to look at the log files where you will see what takes time. For example, does it take a lot of time to solve the relaxation? Then maybe it's a good idea to also adjust the LP parameters, because this is influenced by these parameters, and it's also an important part of the whole process. Sometimes it's difficult to move the bound. So in order to reduce the MIP gap, of course, you're looking for better feasible solutions, but of course you also want to prove optimality. You want to move the bound closer. In a situation like that, for example, you can adjust the cutting plane generation, because that might take a lot of time, and sometimes the bound only moves slowly. So sometimes it's a good idea to adjust these parameters. Moving the bound also means you have to process a lot of nodes. So sometimes improving the node throughput, so changing parameters that more nodes can be processed at the same time, is a good idea. For some models, it's hard to find feasible solutions, not only to find the initial feasible solution, but also to improve existing solutions. So in a situation like that, you sometimes want to spend more time, for example, in heuristics that find feasible solutions or improve existing solutions. Sometimes it's also helpful to change the branching strategy, so the strategy that is used to work through the solution space. There are a lot of parameters here, so we have a few of them here. For example, the branching strategy can be changed with the var branch parameter, and cutting planes and heuristics, so the two most important parameters for reducing the MIP gap, can be changed as well. So cutting plane generation can be reduced, or it can be more aggressive, so that more time is spent in trying to find cutting planes that give a better bound. Sometimes for some models, it's really hard to find initial feasible solutions. So in a situation like that, Gurobi has 3 more heuristics that can be enabled manually, and they are only used if after the root node no feasible solution has been found. And those are pump passes, zero OBJ nodes, and mill rail nodes. So in a situation where you think it's really, really hard to find an initial feasible solution and where you cannot provide a starting solution, it's a good idea to take a look at these parameters as well. So in order to show this a little, we have a few log files, and we take a closer look to see what can be done about it. For example, here's our first example. So this is a typical log file from Gurobi. So this is the tree search. So you see the first few lines, so there are 0 explored and unexplored nodes. So this is the root node. And of course, you can see in the other columns, for example, the best feasible solution so far, the best bound, the resulting gap, and a few other things. And you can also see the runtime in the last column. So what you can see here is the whole process takes some time. So the root node is processed within a second. Then a few solutions are obtained by branching. You can see this with a star on the left side, and then you see a few H. H means that a new feasible solution was found with a heuristic strategy. So what do we see here? We see a run, and after roughly 30 seconds, we got to a MIP gap of 3.71%. And sometimes in a situation like this, it can be helpful to adjust the focus of the search. So for example, you can change MIP focus to 1. In a situation like that, you can focus on finding feasible solutions. So more time is spent in trying to find or improve feasible solutions. Or you can shift the focus more towards improving the bound. So proving optimality is the other direction. And for example, this is the log file for the same model where MIP focus was set to 2 or 3. And what we see here is that for this model, you remember we had 30 seconds when we got to a MIP gap at around 3%, and now we are at a gap of about 3.9%, but after 11 seconds. So it was helpful to shift the MIP focus a little bit towards proving optimality, for example. And this can have a huge impact for certain models. So here's another example. So what do we see here? We are in the root node. So 0 explored and 0 unexplored node, and we find a feasible solution, but it takes 100 seconds, 500 seconds, 1,000 seconds. So we spend many minutes at the same point in the root node, and the bound is moving very slowly. So it looks like we are really stuck at the root node. So remember, the root node is the place where we generate cutting planes and where we try to improve the bound, but of course we also apply heuristics. So for extreme cases, and this is an example, it can be helpful, for example, to turn off cuts completely. So what you see here is, if you do that, is the root node is processed much faster. So it's only around 425 seconds here, and then we already start the tree search. Unlike the previous example, the default, where we spent much more time. And you can see here, after 800 seconds during the tree search already, we find heuristic solutions, and the whole MIP gap is better. It's already with 55%, and in the previous example, it took much longer, and the MIP gap was much larger. It's not only that you have to disable cutting planes in this situation, but for example, there is a parameter that is called improve start time, and what it does is you set a limit. Here it is time, for example, an hour, and what Gurobi does is after this hour, parameters are adjusted within the process. So you reset, for example, heuristic parameters. You focus on improving the solution. So what Gurobi does internally, it changes two parameters. The first one is heuristics. It's set to 0.5, which is a much larger value than the default. So it means spend half of the time about in heuristic, and it also increases the frequency of the rinse heuristic. So what you see here is you have a gap of like 55% after an hour, and then the focus is shifted, and then you see in the next few hours a lot of new feasible solutions are found within heuristics. So sometimes this is also very helpful because you get it to a smaller MIP gap because you spend more effort in finding better feasible solutions. So here's our third example. So what we see here is we see on a Linux machine the top command. And the top command is on Windows, it would be the task manager. You see what's happening on the system. And of course, you also took a look at the log file, and there's not much progress. And if you take a closer look here, you can see that the machine is really short on memory. So what happens is, this is exactly the case that we described in the beginning. The operating system started to extend the physical memory to disk, and this takes a lot of time. So you see that the memory is like 95.3% of the memory is used, but it's virtual memory, and you also see that a lot of SMOP space is used, so a lot of non-physical memory. So in a situation where you don't have this virtual memory, of course the process would have stopped because it was out of memory, but usually an operating system by default will continue to work and extend the physical memory to disk. So this is something that really shouldn't happen in a situation like that. You should really try to move to a machine that has more memory, or use the node file start parameter. So we have this on the next slide, and this is most of the time this is much more helpful than just relying on the operating system. And finally, we have a fourth and last example here. So you see here is a few snippets of a log file, and what you see here is that Gurobi gets to a MIP gap of about 0.01% after 175 seconds. So 0.01% is the default value. So usually it terminates at this point, but for this specific models, because it's rounded, you don't get completely to 0.01, but it's slightly more. And then you see it takes another 2 hours and it doesn't improve. So in a situation like that, the question is really, do you really need 0.01%? Because most of the time, the model itself contains data that has estimation errors. And in a situation like that, you would really want to adjust your termination criteria, because it doesn't make sense to work with data that is maybe was derived using a prediction and that has really some estimated values as well, and then solve it to very small MIP gap. So this may take a lot of time. And the question is, does the solution really help you in reality? Or wouldn't, in a situation like that, it not be helpful to just set the MIP gap to some larger values? So you see, those were just 4 examples, but there are many ways where you can influence the runtime behavior, and the log file is usually a helpful tool where you can determine where time is spent. The important thing is, if you start playing with parameters, don't overtune. So it's not a good idea to collect parameters and use more and more and more. The important rule of thumb here is less is more. And of course, if you use other solvers, do not assume that parameters that were effective for another solver also work for Gurobi. So the internal implementation is likely to be very different. And there's also another thing that is very important. If there is a new Gurobi major release, it's very likely that we learn something. So usually that means you should start from scratch. Tuning, parameter tuning, means you adjust the algorithms to the problem or to a set of problems. And with a new major release, things have changed, or things may have changed. And in a situation like that, it's always a good idea to go back, not modify the parameters, and start with the defaults and see if this works better. Because it's also quite usual that people keep their existing parameters over multiple major release, and in the end, those parameters do not improve runtime as they did a few releases before, but sometimes they even make things worse. All right, so let's move over to our third and last section, which is automated parameter tuning. So what can you do to let Gurobi determine a good set of parameters for your model? So the parameter tuning tool is a part of Gurobi. So it's included within your default installation and you can use it right away. And there are two main ways to use it. And the first one is the command line client. So the name of the tool is GRB Tune, and you can use it and you set a few parameters, and then the tool will work on its own and spend some time in trying to find better parameters for your model or for a set of models. And here is an example on how this could look like. So you call GRB tune, you set a log file where you want the output, then there is the tune output parameter. Tune output equals 3 means you write everything out, so you see the log of each run that is tested. You use 5 different trials. So remember, these are 5 different random seed values. So this is used to handle the performance variability. Then there is the tune time limit, which is 5 days now. It's in seconds. So you spend 5 days for tuning. But you can also set a time limit for the model. So for each model, you run at most for 10 minutes. Then tune criterion equals 2 means you're looking for the best feasible solution within 10 minutes. What you can also do is you can fix parameters. So you fix them and Gurobi will not change them as part of the tuning. So for example, method equals 1 means you always use dual simplex. And then you provide a list of model files that you want to use. For example, here we use 2 MPS files, and that's it. It's not the only way you can use the tuning tool. You can also do it, for example, from the API. If you have a specific model, you can just read it or build it in the usual way. Set a few parameters, for example, the time limit for tuning, which is 1 day here, and then you call, instead of calling optimize, you call the tune function. So those are the 2 main ways to use the parameter tuning tool. You cannot only use it on a single machine, but you can also use them on multiple machines. So the way it works is you start the GRBRS program, which is also part of Gurobi, on different worker nodes, and on the master node, you set the tune jobs and the worker pool parameters. So what you do there is you set the worker pool parameter to a set of host names or IP addresses where these worker nodes can be found, and then all machines will work together on the same set of models for tuning. So the important thing is here, especially if you work with time limits, make sure that the hardware is similar. So if you use very slow and very fast machines at the same time as for tuning, it's likely that the results will not be meaningful because, of course, on a slower machine, the result will not be better within the same wall clock time. The good news is tuning performance scales really linearly. So that means if you have 2 or 3 or 4 similar machines, you can also process 2 or 3 or 4 as many parameter sets at the same times. So that's also how we work here at Gurobi. So we have multiple machines. We always use many machines to tune specific models. And this is really helpful because it allows you to tune in much shorter time using many different machines. If you run the tuning tool, this is how it looks like. So what it does is it tries multiple parameter combinations, and of course it looks for improvements. So you see log output like it's testing a candidate parameter set, and those get numbers. For example, here it's 16. So in this run, the model or the models are run using the parameters MIP focus 2 and var branch 1. And then you see it's solving with a random seed 1, so only with the first trial. But in a situation like that, the runtime is already not so good. It's 3 point something seconds, and the plus sign here says, okay, so this was much longer than an already known parameter set that was already identified, so we just stop there and go on and test something else, because we don't expect that we find something with these parameters. And at the end of the process, you can see the best result when it's finished. For example, here you see the final lines in the tuning log. It tested 20 parameters in 160 seconds. The baseline set was, so with the initial parameters, the average runtime was 0.9 seconds. And with the improved parameter set, for example, here set number 3, it's only a part of the total output. This was reduced to 2.5. So changing the branching strategy here, for example, helped. So this is a typical output, and if you want to learn how to use this tool, you should really use it and play with it and find out what the results are. But again, also, like with manual tuning, the important message is don't overtune. So for example, here is it's a larger example of a bigger model, and what you see here is the total output of the tuning tool. So the baseline run is missing here, but what you see is, for example, you see 7 different sets. So what you see is these sets say, okay, what is the best MIP gap that could be reached by changing 1 parameter? What is the best MIP gap by changing 2, 3, 4, and so on? And it's very important to not just accept the results and use these parameters, but to take a look at the different sets. Some are marked green here, some are red. And red usually means those were random. So they were found, they seem to help a little, but they are not part of the other parameter sets. And this is usually a sign of overtuning. For example, in parameter set 7 here, method equals 0 means use primal simplex. Somehow it was helpful, but it's not part of the other sets. So it's likely that this is just a random observation and it's not a good idea to use it. So it's not robust. And this is also, for example, the case for pump passes 10 in set number 6. It's not in the other sets, so it's probably only a random observation. But if, for example, var branch 0 is part of most of the sets, so it's part of 6, 6, 5, 4, 3, and so on. So this is a good sign that this parameter is always helpful. So this is something that you should consider. And now the interesting question is, which set works the best? Usually, you remember the rule of thumb, we said less is more. So you see the MIP gap gets smaller and smaller and smaller, but not much. So the question is really, should you, for example, for a single model or 2 model, really change 7 parameters? Usually you wouldn't do that because it's very likely that this is overtuning, and if you use a different set of models, they don't work as good as a smaller set. So you should really try to use the smallest possible set in a situation like that. So here's another slide about tuning metrics. So there is a parameter, we already saw that, which is called tune criterion. And what it does, it's the secondary criterion. So the primary tuning criterion is always to minimize runtime. So the runtime that it takes to find a proven optimal solutions. But if you specify a time limit, sometimes the model can't be solved to optimality within the time limit. So you use a secondary criterion. And tune criterion is the parameter that you can adjust for this. For example, you can set it to 1, which is the default. So it says, okay, if the time limit is hit, then go for the MIP gap. Or if the criterion is 2, then go for the best feasible solution found after the time limit was hit, and so on. So this can be adjusted here as well. As a final slide, let's take a look at what we say are best practices for the parameter tuning tool. So be aware of performance variability. So use or pay attention to the tune trials parameter. So the default value is 3 currently. 3 may be not large enough to produce good results. So for example, models with high performance variability, they are very likely to require more trials. Also models that solve very quickly, for example, within fractions of a second, then usually you need more trials because otherwise there's also a danger of overtuning or of having random observations. Then, if you really have a set of parameters that help, try to understand why. find out why this really helps. So take a look at the log file. So for example, if you saw that the bound was moving slowly, you change the MIP focus and now the bound moves better, then it's a good sign. Then you understand why it's helpful. If you have no idea why something helps, usually you should ask someone, or even better, just contact Gurobi support and we are happy to help you with that. Use only parameters that really help. So if you improve performance by 1%, 2%, 3%, it's likely that this is also random. Sometimes, of course, 3% can be a lot, but usually you should only go for parameters that really do a big improvement, like 10% or 20%. Also, again, just to avoid random results. And finally, and this is the last one, of course, this is a statistical experiment. So you search the parameter space, and you usually cannot search the whole parameter space. And the tuning tool tries to do a good search here, but you still need enough time. So examine at least a few hundred parameter combinations. If you just have 10 or 20 or 30, it's likely that there are lots of parameter combinations out there that you haven't tested. And so it's very likely that there is something better out there. Sometimes it's not, but usually spend some time. Especially if your model takes more time, of course, then it takes more time to do some tuning. All right, so that's the introduction to tuning.